For the last installment of section 10.4 notes, the video portion of it at least, here it is. Freezing and melting is the slide I left off on, or at least the next slide. And basically, you'll notice that freezing incorporates a liquid that's going to lose energy. So the energy, you'll notice, is in the product side right here. So the liquid had to lose energy to become a solid. So energy is in the products, okay? And you'll notice freezing point is the temperature at which the solid and the liquid are in equilibrium at 1 atmosphere. In other words, it's got to be standard pressure. Typically, we use atmospheres a lot. That's why it's 1 atmosphere, but any one of those standard pressures. So now the freezing point of water is 0 degrees Celsius. So the freezing point is 0 degrees Celsius. So at 0, solid and liquid are in equilibrium. You had something like this. Solid is becoming liquid. Whoopsie. Solid is becoming liquid. I don't know why I did that. And at the same rate, liquid is becoming solid. So it's in perfect equilibrium at 0 degrees. If I go lower, then I'm past the freezing point, and now I have nothing but solid. If I go higher, then I'm beyond the freezing point in the other direction. I have nothing but liquid. But at 0 degrees Celsius, water freezes and melts at the same rate. And again, at freezing point, solids and liquids have the same kinetic energy, therefore energy loss is in the form of potential energy. In other words, if at freezing point they're going to come together, so in the particles, instead of floating around doing whatever they want to do, they will become a regular arrangement of particles somehow. I'm drawing little squares and stuff like that, but you get the idea. In other words, the particles gain order, and the temperature will stay constant at freezing point until all the freezing is done. And then the moment that happens, then it starts to get a little bit colder. You'll notice melting is the opposite. If I want to get a solid to melt, I better add in energy, and therefore it becomes liquid. Okay? Next slide. Freezing and melting. If I take a pure crystalline substance, now I skipped this in the notes in chapter 10, but a pure crystalline substance, something like an ionic salt, freezing and melting occur at the same temperature. Water is a pure crystalline substance. That's why it's freezing and melting occur at the same point. I don't know any other freezing and melting points, but any pure crystalline substances like ionic solids, freezing and melting is the same temperature. At standard pressure, if solid and liquid exist simultaneously, then the temperature of the system remains constant. So let me explain that. Let's say I got a glass of water, and inside the glass, let's say it's ice water. So you got all these ice cubes in here. And now, if there's ice and water existing at the same temperature for a certain period of time, I know that the temperature inside here must be 0 degrees Celsius because they're existing at the same temperature. So over time, the ice starts to melt and becomes liquid. As long as ice and water are existing together, they will be at the same temperature. It will stay at 0 degrees Celsius. And so more ice melts, it all becomes water, and then finally, once it all melts, then the temperature will start to rise. Okay, it's true, and you can find little anomalies, things to make sure that this works. You got to keep it well stirred. Okay, but other than that, this is absolutely true that a temperature will stay constant during a phase change. Here it is. Temperature will change when either phase change is complete. In other words, temperature stays constant during a phase change. And here's the example which I talked about. Heat up an ice water mixture. What happens to the temperature? You will see that it stays the same temperature. So you take ice. Ice is cold. It gets up to 0 degrees Celsius, and it stays at 0 degrees Celsius until all that ice is melted. Then it starts to rise again. It's crazy, and we can actually do a lab to show that. Molar enthalpy of fusion is like the molar enthalpy of vaporization. Enthalpy is fancy heat. In other words, you have to have constant pressure. But other than that, if you want to change the word enthalpy to heat to make it easier, I don't care. So molar heat of fusion is the amount of heat required to melt 1 mole of a solid at its melting point. And since every substance is a little bit different than everything else, every substance has its own defined molar heat of fusion. You'd have to look it up. And just like it was the molar enthalpy of vaporization, the stronger the attractions, the higher the heat. You have to overcome those strong attractive forces between molecules, and those attractive forces are probably going to be a chemical bond, like an ionic or a covalent bond, or it's going to be some type of intermolecular force, hydrogen bonding, dipole-dipole forces, stuff like that. Okay, if you're, I think that was back in chapter 6, chapter 5, or something like that. Sublimation and deposition. Sublimation is basically skipping the liquid phase, and deposition is skipping the liquid phase. So you'll notice that solid, oops, if I have a solid, you'll notice that if it gains a little bit of energy, it'll go right to vapor. The example of this is dry ice, which is solid carbon dioxide. When solid carbon dioxide melts, it doesn't go to a liquid, it goes immediately to a vapor. Deposition is the opposite, where you take a gas and it goes right to a solid and you skip the liquid phase. The example of this is some of that frost that forms on the surface of your windshield in the morning. That frost was water vapor in the air, and it got cold enough that when it hit your windshield, it became a solid immediately, so it skips the liquid phase. I think this is the last slide here, which is a phase diagram. Very important to interpret a phase diagram. Notice a couple things. Pressure is increasing. Temperature is increasing in this direction. This is, by the way, the phase diagram for water. Oh man, shoot, it's traveling slow here. Sorry about that. Now, a couple things that I want to point out. You notice you have a solid here, a liquid here, and a gas here. So the shaded areas are where these particular phases of matter exist. Any line is going to be an equilibrium point. So along these equilibrium points, along this line I just drew in blue, I have an equilibrium between solid and liquid. Now, what are the points along here? Like, for example, at this point, you have a certain temperature and you have a certain pressure. So at this temperature and this pressure, you will have an equilibrium between solid and liquid. So that's all you have to do is watch these particular lines. This green line is the equilibrium between liquid and gas, and down here, this red line is the equilibrium between solid and gas. So that means at this point, right in the middle, and I'll draw it with a black marker, that point is called the triple point, and that is the only single point where all solid, liquid, and gas are existing at the same point. And there's one little example we can do with carbon dioxide with dry ice, which you can see all three together and then it explodes in your face. But it's really not a big deal. Some other things you want to keep is something called a supercritical fluid. And up here, you're past what's called the critical point. That no matter how high you raise the pressure or how high you raise the temperature, you cannot get back to anything like a gas or liquid. It kind of exists in both phases. Okay? Since this is water, the normal boiling point you can see here is 100 degrees Celsius, and of course that is at 1 atmosphere. Okay, normal melting or freezing point for water is right here. You know it's defined as 0, and of course it's at 1 atmosphere. So that's how we always measure normal boiling point and normal freezing point. It has to be at 1 atmosphere. I think that is it. Any questions, again, come see me. I'll be available all the time, and or email me, and you can find my website online. So talk to you later.